So in this video, what I'd like you to do is to calculate this integral here. And then after you've calculated the integral, I'd like you to differentiate your result and show that you regain the original integrand. So have a go with pen and paper, and then afterwards you can come back and the solution and some comments will follow. So if you just pause the video and attempt the question, and then you can come back. Okay, welcome back. Let's look at the answer on the next slide. So here is the integral, and if you look at it, I think the difficulty is that here we have this root multiplied by an x. If the x wasn't there, you could integrate the root by inspection with a little practice. But this combination is difficult. However, the solution to our problem follows if we think to ourselves, supposing the root was here. So imagine you had an integral like this, 1 minus 2x multiplied by the square root of x. Well, that would be much easier because you would just take this root, multiply it into the 1, and you'd have to integrate root x. And then here you would have minus 2, and then x times root x is x to the 3/2. And again, that is straightforward to integrate. So seeing this and thinking, well, this would be a lot easier, gives us the clue. So the pattern that I hope you are spotting is that we can make a substitution. So if we make this substitution, we can say u is 1 minus 2x, so that this square root will be the square root of u, and x is going to be something which depends upon u. You can just get it from rearranging this equation. And the key formula that we're looking at is this one, and we think, okay, this is f of u of x multiplied by du dx integrated with respect to x. We can write it as f of u integrated with respect to u, and after calculating the integral, we can just replace u by u of x. So here, this is our integral, and we can rewrite u as 1, well, u is defined to be 1 minus 2x. Du dx is therefore just minus 2. If we differentiate that, we'll get 0 minus 2. And since from this equation, if we take the 2x over here and the u over here, we have 2x is 1 minus u. It tells us then that x dividing both sides by 2 is 1 minus u all over 2. So our original integrand can be rewritten as 1 minus u over 2, that's the x, times the square root of u, because this was defined to be u, that was the whole point of this substitution. And then we need to have a pattern where there is a factor of du dx, but here du dx is very simple, it's just minus 2, so all we have to do is write 1 as minus a half times minus 2. Minus times minus is plus, a half times 2 is 1. We'll keep this factor as the du dx that we need for the formula, and this minus a half that multiplies everything, we'll just put it in front of the integral, because that will make the integral look a little bit less intimidating. So our integral is, we're taking this minus a half outside, there is also a factor of a half here, this is divided by 2, so not forgetting the 2 here as well as the minus a half, we pull out a factor of minus a quarter in front of the integral, and then we have the integral of 1 minus u times the square root of u, and the du dx times dx can be replaced by du because of this formula. And this combination is f of u. And now we've got something very similar to the thing that gave us the pattern idea earlier, and we just multiply root u times 1 and minus u times root u, so we have u to the half from here, minus u to the 3/2, u times root u. So to integrate these, Well, after the minus a quarter, we open a bracket because there are going to be two terms. We add 1 to the power here, so u to the half goes to u to the 3 halves, and then we divide by the new power, and that means you multiply by the reciprocal, so we multiply by 2/3. And then here, minus, add 1 to the power, that gives 5 halves, divide by 5 halves, and that's equivalent to multiplying by the reciprocal 2/5. So this is our result for the integral, and now all we have to do is we rewrite our integral in terms of the original variable x, because we know that u is 1 minus 2x. So what we spot first of all is that there is a factor of 2 here and here. So those 2's are going to partly cancel with the quarter, leaving us with a factor of a half. There is a minus sign outside, so when we bring this in, this becomes negative, this becomes positive. I think it's normally safer to write the positive term first, so I'm going to write this one first. So remember, the 2 times a quarter gives a half, minus minus is plus, and a half times a fifth is a tenth. So we're going to get 1 over 10 times u to the 5 halves, which is 1 minus 2x to the 5 halves. Second term is negative. The 2 times the quarter gives us a half times the third gives us a sixth, so we have minus 1/6, and then that is multiplied by 1 minus 2x to the 3 halves because of the 3 halves factor here, and then we will add an integration constant, and that is our answer for this integral. So on the next slide I'm going to differentiate it, but let's first of all just talk quickly through how we did this. So we looked at this integrand here, and we thought this times this is a bit complicated. It's presumably going to be much easier if we had something like this, so we're going to make a substitution to try to move this into being the new variable, which I've called u, and then that just gives this as u plus or minus something, and it turned out that u is 1 minus 2x, so x is 1 minus u all over 2. So you might then say, where is the du dx factor? But in this case, it's just a very simple number, so we can just write it multiplied by its reciprocal. In other words, we've inserted here a factor of 1. And this du dx factor means from this formula, we can just write this as the integral of this times this, integrated with respect to u, and the numbers here and here I've just taken outside. And then these were two straightforward integrals, and at the end we replace the u's by 1 minus 2x, and this is our result. On the next slide I'll verify this by differentiating it and showing we obtain this. If you haven't done that already, have a go at it before looking at the rest of the video. So on this slide, I want to look at our claimed result and verify it by differentiating this and showing that we obtain our original integrand. So here is the derivative of what we have obtained by integration. So we look at this term first. We have 1/10 times this to the power of 5 halves. When we differentiate it, we're using the chain rule, so we're going to multiply by a factor of 5 halves. 5 over 10 will cancel, and we're going to get a half times a half, so we get a quarter. So we're going to obtain 1/4, and then it's 1 minus 2x, we don't change the argument, to the power of 3 halves. We've subtracted 1 from our power, and then we multiply by the derivative of what is in the brackets, and the derivative of this is going to be minus 2. So I'll put that in brackets. I don't want to just write minus 2 without the brackets, because then I mean this subtracted 2. The brackets tell me this is multiplying. And similarly for the second term, we have minus a sixth times 3 over 2 times 1 minus 2x to the 1/2 times, again, the derivative of what was in the brackets, which is minus 2, plus, of course, 0 when we differentiate the integration constant. So we have minus a half, 1 minus 2x to the 3/2, and then here in the second term, the 3 and the 6th would give a half times a half is a quarter, but there's a minus 2 here. Minus minus is plus, and the 2 over a quarter is again a factor of a half, times 1 minus 2x to the half. To combine this and simplify it, because it doesn't yet immediately look like the integrand, we recognize that we can pull out a common factor of 1 minus 2x to the half here and here. And we can also, while we're at it, pull out a factor of a half. And I'm going to write the positive term first as well. So from the positive term, we have a half, brackets, 1 minus 2x to the half, times, and then from this term, there's just a factor of 1. The next term is negative, so we have a minus sign. We've got the half, we've got 1 minus 2x to the half times 1 minus 2x. So we put here 1 minus 2x, close big brackets. So this is our common factor. Here it's multiplied by 1, and here it's multiplied by minus, and 1 minus 2x to the power of 1. We see here immediately that the 1's are going to cancel, and here we have left minus minus, which is plus, and there's a 2, and the 2 will cancel with the half outside. So we're going to be left with plus x from this entire bracket times 1 minus 2x to the half, which means, of course, the square root of 1 minus 2x. And this is exactly what we wanted. This is the original integrand. So this is verifying that our integral was correct. Okay. On the next slide, I want to talk very briefly about how you might have tried to calculate this integral using integration by parts, and you get a result that looks a bit different, but you can verify it using algebra that it's exactly the same as this. And then I will give you a final exercise to look at. So perhaps some of you, when you looked at this integral, tried to do it using integration by parts, and for this integral that method also works. So if we're going to do parts, we look at the integrand and we want to factorize it into a term to differentiate and a term to integrate. We want to differentiate this term, I would say, because if you differentiate it, you're going to get 1, which will make life easier. If we integrate this, we're turning it into x squared, x cubed, etc., and that's probably going to make life harder for us. So we choose u is x, the derivative of u is 1, v prime is this factor, and v is its integral. And if you're going to integrate this, well, this is to the half, so you would expect it to be something like 1 minus 2x to the 3/2. So again, what I'm trying to do is to do this by inspection and just work out what the correct numbers to put here are if any, so that when we differentiate this, we obtain this. So if we differentiate this, we're going to pull a factor of 3/2 in front, reduce the power by 1 to a half, so we'd have the square root of 1 minus 2x, which is excellent. And then we would also multiply by the derivative of this, which is minus 2. So the numbers that we're going to get are 3/2 times minus 2 when we differentiate this. So that the half and the 2 will cancel, and overall we will get minus 3. We don't want minus 3, we just want the root. So we can fix this by saying that the integral of v prime is minus 1/3. And if we're not completely confident, think about what happens if you differentiate this result here. If you differentiate it, you bring the 3/2 in front. The 3/2 and the third partly cancel, leaving you with minus a half. Reduce the power by 1, giving you 1 minus 2x to the half. And then from the chain rule, multiply by that derivative, the derivative of this, and that's minus 2, which would cancel with the minus 2 we have here and from here. So this is correct. So therefore, our integral, which I'm calling I, is going to be, and remember we're using the integration by parts formula, which is that uv prime integrated with respect to our variable is uv minus the integral of u prime v with respect to our variable. So we have all of the ingredients to substitute into this formula ready, so we can just write the answer down. So u times v is minus 1/3 x times 1 minus 2x to the 3/2. That's the product of this and this. And then we subtract from it the integral of u prime 1 times v, which is here. So it's again minus 1/3, but the minus 1/3 we can take outside of this integral. So I'm going to write that as plus 1/3. And then it is 1 minus 2x to the 3/2 integrated with respect to x. And now this integral is one that we can perform by inspection. So what we obtain is that our initial integral is minus 1/3 x times 1 minus 2x to the 3/2 plus, and I'll leave actually the sign as a minus, because if it's going to be plus, I can easily draw the vertical line to turn this into a plus sign. Now, what do we expect? We expect to have 1 minus 2x, I'm leaving a space in front of it, to the power of 5/2, 1 higher power. And if we differentiate this, we're going to bring a 5/2 in front. So I'll just put there a 2/5 to cancel it. We're going to reduce that power by 1. So it will reduce to 3/2. Perfect, that's what I want. And then from the chain rule, we would multiply when we differentiate our answer here by the derivative of this, which is a minus 2. So I'm going to put a factor of a half here, and the minus sign that I've got there already times the minus sign that I get from differentiating this will give us plus, and the 5/2 will cancel, the 2 will cancel, so this will give us 1, but we need a factor of a third here, let's not forget that, so I'm just going to put a factor of 1/3. And if you're not confident, the easy thing to do is now pause, think about it, and differentiate it. So again, when we differentiate this, We would pull out a 5 halves, that would cancel with that. We would reduce the power to the power we want. We would multiply by the derivative of that, which is a minus 2. Minus minus is plus, the 2 times the half cancelled, and the 1/3 that we had there originally is still there. I've written it, so that would give us exactly the integrand of 1/3 times 1 minus 2x to the 3 halves. So this integral is correct, and we now add an integration constant. So now all we have to do is tidy things up a little bit, and we see therefore that our integral is equal to minus 1/3 x times 1 minus 2x to the 3 halves. And then here there's a minus sign. The 2.5 have cancelled, and 1 over 5 times 1 over 3 is 1 over 15 times 1 minus 2x to the 5 halves plus c. And this answer is correct, but it doesn't look like the answer that we had on the previous slide. So here I've just added the result of the previous slide. This term looks like this term, but the number out front is different. This term, however, does not look like this because this just has a number outside of 1 minus 2x to the 3 halves, and here there is a factor of x. So what we have to do is to use algebra to show that this is the same as that. And if you'd like to, you're very welcome to pause the video and try to show how you can get from this to this. Algebra practice is really good for all of us. Okay, so let's see how it would work. So I can write this factor here, minus 1/3 x, as minus 1/6 times 2x. So I've got a minus 2x divided by 6 out front here. And then what I can do is I can add and subtract a 1. So all I'm going to do is rewrite this, and to do it I'm going to say what we have is, okay, so it's 1 minus 2x over 6. I've left a space out front. 1 minus 2x over 6 contains minus 2x over 6, which is minus x over 3, and that is this factor here. But I've added, to make this look like the argument of this brackets, I've added a 1/6, so I have to keep it the same by subtracting a 1/6. So this is minus 1/6 plus that. So I've got that. And this thing, which looks a little bit complicated, it's a way of rewriting minus 1/3 x in such a way that we're just going to have powers of 1 minus 2x. So this is a way of writing this, and it's multiplied by 1 minus 2x to the 3 halves. And then we have minus 1 over 15, 1 minus 2x to the 5 halves, plus our integration constant. So we have minus 1/6 times 1 minus 2x to the 3 halves. I'm now just expanding this combination here. So it's minus a 6 times that, plus this times that. So it's plus, and now it's 1/6, 1 minus 2x to the 5 halves minus 1/15. That's now this term here, 1 minus 2x to the 5 halves plus c. And now this term here is exactly what we obtained here, minus a 6th, 1 minus 2x to the 3 halves. These two terms are both of the form 1 minus 2x up to the power of 5 halves times a number. Sorry, and the number should be plus 1/10. It's this term that we're trying to generate. And what you will see is that 1/6 minus 1 over 15 is equal to, common denominator, this is 3 times 2, this is 5 times 3, so it's 3 times 2 times 5, so it's over 30. 1/6 is 5 over 30, minus a 15th is 2 over 30, so we get 3 over 30, and that is 1 over 10. And the 1/10 is exactly what we wanted here. It's also positive. So these two terms here and here, they are equal to, I'll just squeeze it in here, 1/10 1 minus 2x to the 5 halves. And I emphasize again, I think doing things like this and playing with the algebra and seeing it working is really good for all of us. Okay, so I've shown how to do it in two different ways, using the substitution, which I think for me is the most natural way, and using integration by parts. And on the last slide, I'm going to give you another problem which you can either calculate by using integration by parts twice, or you can calculate by a substitution, and you only need to make the substitution once. So it's very similar to the slide before, and that's the way I would personally recommend calculating it. So I'll show you that on the next slide. So if you'd like to have another exercise like this, you can try to calculate this integral using the methods discussed here. You could use integration by parts, but because this is x squared, you're going to need to use integration by parts twice. I think it's easier to make a substitution, and this is the result you should eventually obtain. And if you wish, you can just pause now, otherwise I'm going to give you a hint about how you would obtain this answer using the substitution method. So, okay, here is the hint. What you're going to do is make the substitution that u is 1 minus x, so that means that x is 1 minus u, so x squared is 1 minus u all squared, and you expand it. When you expand it, you're going to get 3 terms. Each one of them you're going to multiply by a factor of u to the 1/3, and there is of course going to be something which comes from the du dx factor. And when you expand these 3 terms and integrate each of them in turn, you will get these terms. And with that, I will stop this video.